Hello and welcome to this quick clip looking at electrons, orbitals, subshells and energy levels. So on the screen now are three diagrams of helium, neon and argon. You're probably familiar with them from GCSE. You're probably also familiar with the idea of shells and electrons sitting inside those shells. But you might have also spotted at the bottom of each is a new way of writing it out. So what we'll attempt to do is start to answer perhaps what's going on with what's happening in the shaded area. So these are called the electron configurations of the element. So the first thing to notice is that the numbers in superscript add up to the total number of electrons present in each case. So looking at each one, you can see helium has 2 electrons, neon has 10, and argon has 18. So where does the S and the P come from? To clear this up, we have to go back to a little bit about the orbital theory. So going back to GCSE, the Danish physicist Niels Bohr in the 1920s, around 1929, came up with a model of atomic structure that we still use today when we're teaching how the atom is put together at GCSE. However, a little later, German physicist Werner Heisenberg proposed that it's impossible to measure an electron's position or velocity even in theory. This later became known as the Heisenberg uncertainty principle. So because of this, we need to start thinking a bit differently about how electrons were placed. Did they sit in nice neat shells moving in a two-dimensional manner around a central nucleus? We knew there was attraction between the nucleus and the electrons because it was already been proven due to Rutherford's work. This led us to describe the space in which an electron can sit. It's a little bit like a parking space, I suppose. An atomic orbital, as we call it, is a region of space around an atom's nucleus which can hold up to 2 electrons. So lower energy electrons in a shell tend to occupy what we call s orbitals. So it's a sphere, and anywhere within that sphere the electrons can exist. So it's always assumed that the nucleus sits in the centre of the orbital. So it's a spherical space around the nucleus in which the electrons can exist. And a sphere is a uniform size throughout, so equal probability that electrons can be found anywhere inside this space. So a p orbital has a figure of 8 shape. So what this means is that the wider part at the top and the bottom is where you're more likely to find electrons, in the 2 locations that are pointed to by the 2 red arrows. So p electrons have greater kinetic energy than s electrons, so are more likely to be found further from the nucleus as they repel each other. So that's why one end of the orbital is slightly fatter than the middle end, because the probability of finding it in the outer edges of the orbital are much higher than finding it in the middle. So we need to also look at the positioning of p orbitals. So if you consider that the p orbitals, each of which can hold up to 2 electrons, can sit in one of 3 possible axes, we can now start to put all this together to match what we've learned at GCSE. So considering that an s orbital can have 2 electrons if it's filled, and 3 p orbitals, if they're all filled together in that way, have 6 electrons, we now have 8 electrons in total. So we now have our 8 electrons needed to fill a shell, just like we've been taught at GCSE. So it's important to point out that S and P are not the only kind of orbitals. Some of the elements in the periodic table have very, very large atoms. And to accommodate this fact, we also have d orbitals and f orbitals. So the elements in the periodic table are organised into blocks at A level and beyond, according to which type of orbital is being filled at the outer shell. Is it an s orbital? Is it a p orbital? Is it a d orbital? Or is it an f orbital? And because as atoms get bigger, they contain more and more and more electrons, what we do is we take the orbitals that contain electrons that have similar amounts of kinetic energy and we group them with others which contain electrons of similar kinetic energy, and these groupings are called subshells. So some subshells have slightly higher energy than others, even though they exist in the same shell or energy level, shown here as N. So if we just focus on boron for a second, we can see we've got a p subshell existing at slightly higher energy than the s orbital in the same shell. So you can compare the p subshell to the s orbital, but both can be found in energy level 2, or shell 2. And you can find a similar pattern across the other elements in the same block of the periodic table. In this case, if you check your periodic table, you'll see quite clearly it's the top part of the p block. So let's look at the order in which the orbitals are filled. It's important we follow the correct convention. So lower energy orbitals always fill before higher energy ones in a given energy level or shell. So therefore s orbitals fill before p, p before d, and d before f. So electrons will avoid pairing up in the same orbital if there's space in another orbital in the same subshell. And this is commonly found in p, d, and f subshells. And you can see that clearly illustrated in the boxes that show the positioning of the electrons. It's also worth pointing out that 4s fills before 3d, as their energy levels are actually very similar. So the energy levels of 4s and 3d overlap, similar for 5s, 4d, and in subsequent energy levels. And if we take a diagram from a little earlier in the clip, we can see there's an energy overlap between 4s and 3d, which helps to explain this. So as we've covered quite a lot in the last 7 minutes or so, it's now time to switch off the video and see if you can practice some examples from your textbook to try and reinforce some of these ideas.